afternoon and welcome to the first James R. Thompson Leadership Lecture at the Illinois Mathematics and Science Academy. My name is Don Nordland, and I have the privilege of serving as Executive Vice President of the IMSA Fund for the Advancement of Education, which fund board is headed by Governor Thompson. The IMSA Fund is a not-for-profit corporation that enlists private sector investments in the Illinois Mathematics and Science Academy. As most of you know, IMSA is the nation's only three-year public residential high school for talented mathematics and science students. Equally important, the Academy serves as an educational laboratory for developing and testing innovative programs to share with other schools, school districts, teachers, and students in Illinois and in the nation. Private sector gifts provide margin of excellence resources for IMSA. Last year was our most successful fundraising year. Corporate, foundation, and individual donors gave $780,000 to the IMSA Fund, a 42% increase over the previous year. The James R. Thompson Leadership Lecture Series is just one example of programs made possible by these private gifts. At this time, it is my privilege to introduce the talented and visionary leader of this pioneering educational institution, IMSA's Executive Director, Dr. Stephanie Pace Marshall. Stephanie?
Thank you, Don, and good afternoon. This is a very special and proud day at the Illinois Mathematics and Science Academy. And on behalf of the Board of Trustees, the faculty, staff, and students of IMSA, welcome to the Academy and to the inaugural James R. Thompson Leadership Lecture. At a time in our nation's history when national and international attention is once again focused on achievement in mathematics and science, it is indeed fitting that our first Thompson Leadership Lecture would focus on science and its contributions to human understanding, and would feature one of the world's foremost science scholars. At this time, I would like to recognize several very special friends of IMSA. First and foremost, the man in whose name this lecture was established, and one of those in whose honor this school was dedicated. Please join me in extending a very warm welcome to Governor Jim Thompson and his wife, Jane. I would also like to recognize two special advocates of IMSA, Senator Forrest Etheridge and Representative Suzanne Deutschler. Both have been strong supporters of the Academy and indeed education in all of Illinois. We are delighted that they could be with us today. Forrest, Suzanne? It is also my pleasure to bring you greetings from Governor Jim Edgar, who was not able to be with us today, but he has sent a letter and I would like to read it to you. My friends, as Governor of the state of Illinois, I am very pleased to extend a personal greeting to everyone attending the first James R. Thompson Leadership Lecture presented by Dr. Carl Sagan. Illinois' most valuable resource is our young people, and I commend the vital role Dr. Sagan is playing in nurturing that source. I am certain this enriching, rewarding experience will result in new ideas and developments. Education is a lifelong process, and it is my hope that you will continue to take advantage of all future educational possibilities as you, our stars of tomorrow, strive for excellence. With best wishes, Jim Edgar, Governor. We are also very pleased to have with us members of the IMSA Board of Trustees, the IMSA Fund Board of Directors, the Alliance Council, and local government officials. And finally, we are delighted to welcome our corporate foundation and individual donors to the IMSA Fund. We thank you for your generous support, and we look forward to forging even stronger partnerships with you. At this point, it is now my great pleasure to introduce Walter Lee, the President of the IMSA Student Council.
Thank you, Dr. Marshall. Good afternoon. On behalf of the student body, faculty, and staff of the Illinois Mathematics and Science Academy, it is my pleasure to welcome our special guests from various schools of Illinois. We are truly delighted to have with us student representatives from our neighboring high schools in Aurora, and to welcome our 1991 IMSA Junior Scholars who come from various schools in Illinois. In addition, I would like to welcome those teachers from throughout the state who are participants in IMSA's Summer Adventures and Impact 2 programs. Each teacher was invited to bring his or her principal and a student, and we are pleased to have you with us as well. It is also my pleasure to welcome some very special members of the IMSA community, those parents, alumni, and alumni parents who are with us here today. And finally, last but not least, welcome to the members of the media. We appreciate your interest in education, science, and IMSA. Again, welcome to all of our guests. I hope you enjoy the first James R. Thompson Leadership Lecture.
Thank you, Walter. It is now a privilege and pleasure for me to introduce our speaker today. Dr. Carl Sagan is the David Duncan Professor of Astronomy and Space Science and Director of the Laboratory for Planetary Studies at Cornell University. He is President of the Planetary Society, the largest space interest group in the world, and is a distinguished visiting scientist with the Jet Propulsion Laboratory at Caltech. Dr. Sagan, as you know, has played a leading role in the Mariner, Viking, and Voyager expeditions to the planets. His scientific research has enhanced our understanding of the greenhouse effect on Venus, dust storms on Mars, the organic haze on Titan, the origin of life, and the search for life elsewhere. For 12 years, he was editor-in-chief of Icarus, the leading professional journal devoted to planetary research. In addition to more than 600 published scientific papers and popular articles, Dr. Sagan is author, co-author, or editor of more than 20 books. His Emmy and Peabody award-winning television series Cosmos has been seen in 60 countries by more than 400 million people. His accompanying book, also called Cosmos, was on the New York Times bestseller list for 70 weeks. Dr. Sagan and his colleagues have been engaged in research on the long-term consequences of nuclear war, and partly for this work, he was given the annual awards for public service of the Federation of American Scientists and of Physicians for Social Responsibility. He has received numerous other awards, among those 18 honorary doctorates from American universities. We are honored and most fortunate that Dr. Sagan also serves as a member of the Illinois Mathematics and Science Academy's National Advisory Board, and it is that reason that he is with us today. Several years ago, in speaking about the importance of IMSA's mission, Dr. Sagan said the following, and I quote, "The need to understand how the universe works is fundamental to human nature. It is also essential for safely managing the human future, but foolishly we have designed a society based on science and technology in which hardly anyone understands science and technology. This is a clear prescription for disaster. Our future depends on producing and encouraging highly competent, ethically responsible young scientists, as well as much greater scientific literacy in the general public. The Illinois Mathematics and Science Academy in Aurora, Illinois, is dedicated to meeting this challenge. It is a gift from the people of Illinois to the human future. Today, I am honored to introduce a man who has dedicated his life to advancing scientific knowledge, promoting the ethical applications of science, and increasing the general public's understanding and appreciation of the beauty, wonder, and mystery of science. I don't know how technical and detailed Dr. Sagan will be in his remarks, but just in case you cannot comprehend or recall all that he will tell us today about comets and the origins of life, I came across a crystal clear explanation that should assist us. It was in the Sunday Comics 2 weeks ago in the comic strip Mr. Buffo. Proudly displayed on Mr. Buffo's t-shirt was the following statement on the creation of the universe attributed to Carl Sagan. It was late. It was dark. Things happened fast. Would you please join me in welcoming one of the world's premier astrophysicists, Dr. Carl Sagan.
Excuse me, on the lights.
Right here.
Yeah. Can we have all of these lights on? All of these overhead lights?
Don't cause a sound problem. The mercury vapor will cause a real bad buzz because of the magnetic field that's created.
Thank you, Dr. Marshall, for that generous introduction. What we've been talking about here is with the lights, a lot of lights on me and only a little bit of light on you, you can see me, which you may or may not be happy about, but I can't see you, which I'm unhappy about because I like some feedback loop with the audience. So I'm hoping that we can have a little more light in the audience and these lights on me off. That's good. I'm really pleased to be here with you. I will not spend any time explaining to you why it's important for people to understand science. For one thing, Dr. Marshall quoted me on it, and for another thing, you wouldn't be here if you didn't understand that yourself. What I'd like to do is to talk about a subject which in a way is extremely fundamental, is wonderfully interdisciplinary, and about which we are actually beginning to learn something that it might not have been true. We might have been wholly ignorant about this fundamental subject, but we've been lucky. And the subject is the origin of life. Now, what are we talking about when we talk about the origin of life? If we look at life around us, and I don't just mean the students at this institution, but all the life on Earth, we see what seems to be a wonderful diversity, all the beasts and vegetables and microbes. And if the Earth were only a few thousand years old, as people believed for a long time by adding up the begats in the book of Genesis, then the idea that some organisms evolved from other organisms, evolving from very simple organisms, that was just a silly idea, and hardly anybody believed it, and for good reasons. But if, as we now know, the world is 4.5 billion years old, as we know beyond the shadow of a doubt from radioactive dating, among other methods, then there is time. And the critical insight into what was possible if the world was very old happened in the epical publication in 1859 of Charles Darwin's book, The Origin of Species. And there, Darwin proposed a mechanism by which evolution could occur. It's at once ruthless and heartless, and at the same time subtle, intricate, beautiful. He called it natural selection. The idea is extremely simple, and all you have to do is just think about it for a few minutes, and it's clear something like that has to be true. And it goes like this. If children resemble their parents in their hereditary characteristics, if young animals and plants resemble their parents, if there is a hereditary transmission of information, and if that information is subject to any kind of variation of the sort that we today would call mutations, then there will be slightly different organisms in each generation from the previous generation. Some of those organisms, by accident, will be better adapted to the environment, some will be less adapted. And the differences might be very tiny. The differences might have to do with biochemistry, or length of the bones, or ability to run fast, or breathe air, or resist disease, or anything. If also organisms reproduce rapidly, so that under the best conditions there get to be huge numbers and therefore competition between organisms is established, then natural selection will favor certain organisms and do the opposite for other organisms. There will be a steady progression of change. Certain mutations will be selected for, certain other mutations will be selected against. And this winnowing, the organisms selected against die or don't live as long, or at least leave fewer offspring. And so working in this way, small changes every generation, over an enormous period of time, major changes in life can happen. And if you think about the lifetime of human beings compared to the lifetime of the planet, maybe the average person is a few decades old. The Earth is a few billion years old. So the average person lives for 100 millionth the age of the planet. And therefore, how could we possibly understand from what we ourselves see in our own lifetime the progression of evolutionary change? To understand that, you must go to the fossil record. And so Darwin not only recognized the principal mechanism for evolution and its power, but also proposed, rather diffidently, before he got into that line of work, he had intended to be a minister, a preacher in the Church of England. He proposed that humans, as well as all the other beasts and vegetables, had evolved. That humans came from a non-human primate ancestor who would look certainly something like an ape to us if we were introduced to him or her. That our primate ancestors evolved from other mammal ancestors, the mammals from reptiles, the reptiles from amphibia, the amphibia from fishes, and so on back to some very simple organism that was the ancestor of everybody on Earth. And in that sense, incidentally, stressing a deep kinship of all the plants and animals on Earth. We're all cousins. And it was Darwin who first explicitly stated this by a mechanism which actually makes sense. But you might think this doesn't explain some things, but it doesn't explain the fundamental question, because where did that first ancestor come from? And there Darwin was stumped, or almost stumped. There is one curious line he wrote in a letter to his friend Joseph Hooker, who was the president of the Royal Society of London, which went something like this: if only, Darwin said, we could imagine a warm little pond somewhere in the ancient history of the Earth in which certain molecules were interacting, and then dot, dot, dot. And he even said what some of those molecules might be. And they are what we call organic molecules, plus, he explicitly said, ammonia, plus phosphates. For 1870 or so, this is a remarkably good insight, even though it was something he never actually published, just in private correspondence. So Darwin had the idea that the origin of life was connected with the origin of certain organic chemicals. Now, all of life today, on this planet at least, is based upon one category of molecules called the nucleic acids. And the nucleic acids encode, supervise the construction of another category of molecules called proteins. And certainly life on Earth is mainly the business of nucleic acids and proteins. If we could understand the origin of nucleic acids and proteins without pre-existing life, we would certainly be making a substantial step forward towards understanding the origin of life. It's not the same thing. If you have the building blocks just lying around, that doesn't mean you have a living thing. But if you look more closely, you see that the nucleic acids are, in a way, self-replicating molecular systems. Under the right conditions, they make identical copies of themselves. If you could imagine an early organism which was no more than a molecule that could make copies of itself, then you might be there, or pretty close. If you had a molecule which could crudely make copies of itself, then there would be mutations, the replication would not be perfect, cosmic rays would produce changes in the molecule, and so then the next generation that molecule would copy would be changed in that direction. Well, that's all you need. If you have replication and mutation, natural selection is working. And since we know that the nucleic acids are self-replicating, it's a very major step towards understanding the origin of life if we can understand the origin of these particular molecules. So I want to stress, it's not the same thing, but it's a major step there. So, okay, where did this stuff come from 4 billion years ago? I say 4 billion years ago because we know the epoch of the origin of life pretty well, better than 10% accuracy. And the argument goes like this. The earliest fossils we know are about 3.5 billion years ago, although the carbon isotope chemistry from sediments that are 3.8 billion years ago maybe indicate the presence of life even then. It's hard to find fossils back then because there's hardly any pieces of continents that date back that far. So there's a paucity of the geological record, and it might be that there are fossils a little bit earlier than that. The earliest fossils we have are of colonial microorganisms, and so that's fairly advanced. They could not have been the first organisms, and so there had to be a substantial period of time Before that, for the first organism. Then running the other way, the Earth at the time of its formation was a very inhospitable environment because the Earth fell together, pieces from the sky, and in the process was melted and produced a steam atmosphere. And the pieces that made the Earth continued to fall, and in a certain sense they're still falling today. Every impact of a comet or an asteroid, which I'll come to shortly, is in a way the very tail end of the distribution function of the falling together of the Earth. And in the early days, before the solar system was cleaned up by collision, stuff was falling from the sky all the time. And big things falling from the sky, you can see, might make the Earth an unpleasant place, especially if it would melt large areas of the Earth. And even by 4 billion years ago, there were occasional massive impacts. By 4.1 or 4.2 billion years ago, sterilizing impacts that would just sterilize the whole ocean or vaporize the whole ocean and send it off into space were still occurring. So you can see the time of the origin of life is bounded. And it's maybe between 4.2 and 3.8 billion years ago. Roughly speaking, we'll call it 4 billion years ago. And there's some people who think that if the origin of life happened quickly, in terms of the geological time scale at least, that maybe it's a probable event. Maybe you just set the conditions right and pow, life arises. Now, nobody has ever done an experiment in which you, I don't know, mix together the gases and waters of the early Earth and have stuff fall in from the outside maybe, and shine ultraviolet light and zap it with electrical discharges for a while, and then at the end of the experiment, somebody crawls out of the reaction vessel. Nobody's managed to do that. We're very far from that. But on the other hand, making the building blocks of the proteins and nucleic acids, there, as I will explain, we've been very successful. You know, there's a strange sense you have lecturing here, and that is every time you wave your hands, there's a bright light that goes off. It's the most remarkable correlation. And when I leave here, I'm going to have this disappointed sense of a sort of superpower lost, you know? William Huggins was a mild-mannered 19th century astronomer who scared the world. He didn't mean to. He was just minding his own business, which was spectroscopy. But one thing led to another. You can never tell what's going to happen if you're a scientist. Your very arcane, abstruse work may suddenly have all sorts of social relevance, and you better be ready for it. So here's what happened. He was a pioneer. I'm going to take off my jacket. He was a pioneer in looking at astronomical objects, having the light from them pass through a telescope and then a spectrometer which dispersed the light into its constituent colors, and then recognizing the signature, the pattern of absorption lines, which gave you some idea of the chemistry of the source, often of reflected sunlight off a solar system object or emitted light from a distant star. He succeeded in recognizing some of the atoms in distant stars. He looked unsuccessfully at planets, and sort of as a fluke, he looked at comets. And he found a set of absorption lines in comets which were different from those in stars. And couldn't figure it out for a long time what it was. And then he and some French scientists the French scientists must have been especially good at this, thought to look at the absorption spectrum of olive oil, which I imagine was sitting around more in the French labs than in the English lab of William Huggins. And to their amazement, olive oil looked like comets. Now, if only it were true, we would have an economic motivation for spaceflight that is missing today. But what it turned out was not that there was olive oil there, but that if you vaporize and dissociate olive oil, you produce a molecular fragment, C2, two carbon atoms attached to each other, which is also up there in the comets. And so, although they didn't use this word exactly, this was evidence for organic matter in comets. Organic, of course, merely means a molecule based on carbon. It doesn't mean of biological origin. There are astronomers who refuse to use the word organic because they're worried that people will misunderstand that it means of biological origin. And a colleague of mine calls it the O word. And you find all sorts of circumlocutions that astronomers use, including they say carbonaceous, carbon-containing, and then after the experimental results on Halley's Comet, a new phrase was introduced, CHON particles, C-H-O-N, carbon, hydrogen, oxygen, nitrogen. It's a major effort to avoid saying the word organic. But I hope it won't offend anybody. I'm going to just use the word organic, as chemists routinely do. Well, so Huggins discovered some organic matter in comets, big deal. But he continued over the years, and then in the 1880s, he found evidence for not the molecular fragment CC, but the molecular fragment CM, the nitrile radical, except it has another name. Names count in this business. The other name is cyanide. And, but nobody paid much attention to that until just before 1910. Because in the year 1910, first slide please, the Earth was predicted to pass through the tail of Halley's Comet. I'll of course need the lights down with the slides around. Thank you. There's a small intelligence test posed to me here, turning off the light. This light, well, I failed the test. So this is the idea. The tail of the comet pointing away from the sun, the Earth, thank you, passing through the tail of the comet, and then people suddenly thought, my goodness, there's cyanide in the tail of the comet. Prussic acid is potassium attached to the cyanide radical, and a single grain of prussic acid on your tongue can kill you. So the idea of enormous quantities of cyanide in the tail of the comet, the Earth passing through it, scared lots of people. There were sustained national panics in Japan and Russia. 100,000 people in Constantinople ran to the rooftops in their nightclothes. People in Chicago stuffed rags and newspapers under their doors. The Pope banned the hoarding of cylinders of oxygen in Rome. A smattering of people all over the world committed suicide because they didn't want to die by poison gas. And poor William Huggins was responsible for all of this. And he had never talked to a reporter in his life. Now, what's more, there were lots of scientists who said, wait a minute, it's not even clear that the Earth is actually going to pass through the tail of the comet, and if it does, we can calculate what the density of cyanide radical is, and it'll be at the very most 1 part per trillion. of stuff in the air, and you can breathe that amount of cyanide. It's not that one atom of cyanide will kill you. And people said it's less dangerous than breathing the noxious atmosphere of London. But that did no good. Once the idea was in the public mind, people got tremendously worried. Well, except for the people who committed suicide, nobody died in 1910 because of Halley's Comet, except for the fact that William Huggins died in 1910. But not from cyanide. He was 85 years old. Well, the curious fact is that the molecule in question, hydrogen cyanide, is a key precursor for the synthesis of amino acids, the building blocks of proteins, and the nucleotide bases, the building blocks of nucleic acids. It's a really strange fact that this molecule, which can kill you if you happen to be an oxygen breather, might in fact have been central for the origin of your distant ancestors. And I'll come back to that shortly. What I'd like to do now is to give just a quick sense about what comets are and talk about their involvement in the origin of life. Next slide, please. This is a montage of the views in various cultures of what they saw when a comet came by, except for the last two before the era of the telescope. And you can see that that people had quite different views, including this, as you might guess, medieval rendition, which was that a comet looked like a sword. Even here, comets are psychological projective tests. There's a few other representations of comets I haven't included here. People see what they're sort of interested in. But what was it? Most people thought that either it was something, it was a sign sent by God to warn us of impending disaster. And that's always been sitting on the edge of scientific interest in comets. Or Aristotle's view that it was a sort of meteorological fire in the upper atmosphere, an exhalation from the interior of the Earth that stayed fiery in the air. So the question is this something in the Earth's atmosphere, as almost everybody thought, or is it something astronomical? In the 16th century, the Danish astronomer Tycho Brahe, Johannes Kepler's teacher, realized that there was a way to answer that question. Next slide, please. If you had two widely separated observing stations on the Earth, and the comet was low, close to the Earth, in the atmosphere, then this guy looks at it and will see it against one background set of stars, one constellation, and this guy looks at it and sees it against a different background. And therefore, there's an excellent way to see if it's down low. If, on the other hand, it's far away, next slide, please, then two widely separated stations will see it more or less against the same background. And this method, which is known as parallax, and which many of you probably know about, not only works qualitatively, but it works quantitatively. By the relative shift against the background stars, you can tell, in fact, how far away it was. Well, Brahe organized a cooperative international program to examine a comet and found beyond any doubt that the comet was beyond the moon, translunar distances, which everybody thought really bizarre, especially because the prevailing religious doctrine was that nothing could change in the heavens. That was one of the main reasons people wanted comets to be down in the atmosphere. But it's mathematics, hard to say no to. What a comet, in fact, was not for Tycho Brahe to figure out. And this was, I'll come to it in a moment, an insight provided by Edmund Halley. But let me show you what the contemporary context of comets is. Next slide. So here's a schematic of the inner planets of the solar system: Mercury, Venus, Earth, Mars. And this scale is 1 astronomical unit. There's something pathetically chauvinistic about astronomers deciding that the Earth's distance from the sun is an astronomical unit. You know, measure the whole universe by our distance from the sun. But it's a kind of conceit that we have to live with. Well, the Earth is 1 astronomical unit from the sun by definition. And here is a so-called short period comet, which you can see lives more or less in the inner part of the solar system. Next slide. This scale is 100 astronomical units, so everything we saw in the last picture is within this little square. And so here's the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. And this highly eccentric or elliptical orbit is the orbit of Halley's Comet, which, as you see, lives part of its time out beyond the orbit of Pluto. The next slide increases the scale to 1,000 astronomical units. Everything we saw in the last one is in this little square. And here is the orbit of a not unusual longer period comet called Comet Mercosur. And it mainly lives far beyond the planets. And it intersects a very interesting regime into which no spacecraft has yet ventured, in which the cometary nuclei, silently frozen, orbit the sun. And if we go out to the next step of 10, next slide, to a 10,000 astronomical unit scale, then we find ourselves in what is called the Oort cloud of cometary nuclei, a spherical cloud of maybe 1 trillion comets, typical size of one maybe a kilometer across, that orbits the sun. Every now and then, a passing star or a passing interstellar gas and dust cloud shakes up the Oort cloud, makes a ripple, and occasionally a comet will be redirected in a new orbit down into the inner solar system, and there's a new comet in our skies. What's more, the short period comets were probably captured by the planets in the inner solar system from original long period orbits. So the comets come from halfway to the nearest star, by and large. They are visitors from the interstellar dark. They're not the same as the stuff in the solar system. The fact that they might be carrying organic matter is made doubly interesting by the distance of their origin. Next slide. Here is now, for the inner solar system, this is the orbit of Jupiter, a small fraction of the set of orbits of comets. Look how many there are. Look how the orbits all intersect each other. And it's very clear that if the Earth is orbiting something like this once a year, and these guys are bopping in and out once every few years, and the Earth lives for 4.5 billion years, that you can't avoid some of these guys bumping into the Earth. Collisions with comets are just unavoidable. And as you go back earlier in the history of the solar system, it's much more unavoidable. Next slide. Comet is made mostly of ice. Every time the comet comes close to the sun, about 1 meter thickness of the ice evaporates. And eventually, after enough perihelion passages, all the ice is gone. And so all that's left is the non-icy stuff, mainly rocky material and organics. And some of that becomes fragmented. And so what you have is the orbit of the comet begins to be filled up with these fine particles, the whole orbit. Each fine particle is a separate little comet or planet circling the sun. Well, if the Earth plows through that orbit, these fine particles are going to enter the Earth's atmosphere. Within a certain size range, the small guys burn up, ablate away in the upper atmosphere, mainly about 100 kilometers up. And so, when you're outside walking on a clear, moonless night, maybe at the time of the Perseid meteor shower, and you look up and you see a lovely little flash, that is a piece of a dead comet in its last moments before being dissipated into atoms. And I think that's a much more poignant and lovely and realistic view than the other view, which is that it's something the size of the sun falling into the Earth's atmosphere, right? A falling star. Think of how that phrase is built into the language and into poetry, and what an erroneous view of nature it carries with it. In the same sense that the words sunrise and sunset are pre-Copernican. They are words that come from a time when everybody imagined the Earth was stationary and the sun was moving, rather than the other way around. The language has fossils in it, as well as the geological record. The next slide shows that bigger objects entering the Earth's atmosphere also burn up. This is called a fireball. And a number of UFO reports are due to pieces of comets larger than the dust-sized or pea-sized objects that make meteors. Very little particles float down like a fine rain. They are slowed down so quickly that they do not burn up. And very big particles, massive objects, boulders, city-sized objects, will traverse the Earth's atmosphere and make it to the surface without much burning up. There will be an ablation crust on the outside that will burn up, but the body of the thing will make it to the surface of the Earth. I'll come back to that as well. Next slide. Now, pieces of comet come to us, as I've been saying, but they mainly burn up. It's hard to get a piece of a comet. We also fly airplanes at stratospheric altitudes. A message is being sent to me, but we also fly airplanes at stratospheric altitudes with the kind of flypaper on their wings to catch dust particles from comets. It's very hard to grab a piece of a comet. So, in addition to the comets coming to us, we can go to the comets. In 1986, Halley's Comet made its next return to the Earth after the Huggins 1910 apparition. It orbits the sun every 76 years, so 10 plus 76 is 86. Just like clockwork, it was back. But by 1986, for the first time, the human species had invented a means to go and greet Halley's Comet and find out what it was. So there were two Soviet spacecraft. This is a representation of one of them, called Vega, that carried a set of instruments from 17 European nations, plus the one American instrument which got aboard despite the best efforts of the Department of Defense to prevent it. A European spacecraft called Giotto, which had contributions from 13 European nations, and the first two interplanetary spacecraft of Japan. They were more elementary spacecraft, and they flew by at a greater distance. Conspicuous by its absence was a spacecraft from the United States. It was voted down in the White House because it was too expensive. it would have cost as much as a single B-1 bomber, of which we were then committed to purchase 100. 99 would have compromised national security. So, as a result, there are no American spacecraft by Halley's Comet. And, this may be a chauvinistic remark, as a result of that, there are missed scientific opportunities about understanding Halley's Comet. The Soviet spacecraft, and especially the European spacecraft, Giotto, got very close. Giotto got within a few hundred kilometers of the nucleus of the comet. See, there's a solid object in there, and then there's a fuzzy cloud of gas and dust called the coma, and then the gas and dust is blown back by radiation pressure and the solar wind to form the long and lovely tails of comets. And what we see from the Earth is a little bit of coma and mainly tail, and the nucleus hiding in there, that nobody has seen. What these European and Soviet spacecraft did is fly through the coma, almost colliding with the nucleus to see what the nucleus of a comet looks like. And the next slide shows you. This dark, shadowy, peanut-shaped object, it's about 10 kilometers across, long dimension, is the nucleus of Halley's Comet. It's very dark. The amount of sunlight that it reflects back is something like 3 or 4 or 5%. That's very dark. That's as dark as black velvet. And that is, in fact, one piece of evidence for worked organic matter. And what you're seeing here are jets of ice blowing off the comet, heated by sunlight, vaporizing, carrying dust in it, and that will later form the tail. The next slide is, maybe you can see it a little bit better. I recognize people in the back. Some of this may be hard. I apologize for that. But you can see, maybe more clearly here, the nucleus of Halley's Comet. Now, there were instruments on board these spacecraft to look for chemistry, something like a mass spectrometer. And what is very clear is that Halley's Comet is rich in organic matter. It's made, in fact, about 25% of a variety of organic molecules. The trouble is, for technical reasons, which, if anybody's interested, I can outline in the question period, the reliability of specific identification of particular organic molecules is weak. But that they're organic is clear. Okay. So, if comets are loaded with organic matter, if comets hit the Earth today, there was a little one that hit Siberia in 1908, and if they hit the Earth with much greater frequency at the time of the origin of life, maybe organic matter played a role in delivering to the Earth the stuff from which life emerged. Next slide. So here is an artist's conception. This is the Japanese artist Kazuaki Iwasaki. Lovely picture of the Earth around 4 billion years ago. The moon is closer to the Earth then, so it looks bigger in the sky. And what is represented here is that there's stuff falling from the outside, exogenous material, and stuff generated, in this case from lightning, on the inside, down here, endogenous organic matter. Right? Exogenous, the XO is the same root as exit, meaning out. And endogenous, the endo root is the same as entrance. So molecules from up there, molecules from down here. What is the relative contribution of these two? Next slide. This is a schematic representation of a mechanism of the production of amino acids, the building blocks of proteins, as fully demonstrated in the laboratory, if the Earth were hydrogen rich. The universe is hydrogen rich. The giant planets are hydrogen rich. Hydrogen rapidly escapes from the Earth. it is plausible that the early atmosphere of the Earth had a lot more hydrogen than it does today. So up there is water. This guy and this guy is methane. This is ammonia. If such molecules are struck by ultraviolet light or charged particles, they fall to pieces. The radicals recombine. You can see the pieces here. And two of the principal products are, guess what? Hydrogen cyanide, HCN, and there's an atom right there you can't see very well, formaldehyde. And these two materials, cyanides and aldehydes, together with the ammonia in the air and the water in the oceans, readily form with high yield amino acids. So there's something quite remarkable. You take very common stuff, very simple molecules, apply any energy that breaks them into pieces, and then they recombine and form some of the molecules of life. Wouldn't have to be that way. And we learn something from the fact that the laws of physics and chemistry permit this ready synthesis of the building blocks of life. Next slide. Well, you can calculate how much ultraviolet light there was in the early environment of the Earth, measure in the laboratory the efficiency of production of organic molecules, and then integrate and get the total amount that must have fallen. Of course, molecules fall to pieces as well as being synthesized, and so you calculate what the steady state abundance of organic matter could have been, in this case from ultraviolet light, an endogenous source. Next slide. Endogenous production of organic matter is happening today. It's not on the Earth, because we have an oxygen atmosphere, but on Titan, the big moon of Saturn, where the Voyager spacecraft found gas phase simple organic molecules, including HCN, and this pinkish, impenetrable cloud layer is made of complex organic solids. And those solids, if you drop them in water, make lots of amino acids. And in similar experiments, the building blocks of the nucleic acids are also produced. So it may be that on Titan, in a frozen state, is an enormous amount of the products of pre-biological organic chemistry, the stuff that 4 billion years ago on the Earth led to the origin of life. Maybe not gone very far on Titan, because ordinarily there should be very little liquid water there. The surface temperature is 95 degrees above absolute zero. But on the other hand, through cometary impacts and maybe through some tectonic activity, there may be episodic melting of ice, and maybe there is a little liquid water chemistry there. We don't know. We hope to land there sometime early in the next century. Back to Earth. Next slide. So that was about endogenous, now about exogenous. This is a picture, of course, of the moon. You can see Aurora, Illinois right there. And as you well know, the highlands, the uplands of the moon, are cratered, but saturation cratered. So craters fall on top of craters, and the whole surface is full of craters. And there's no erosional processes on the moon, or almost none. So we are looking back to very early times. The moon is an impact counter. And since the moon is close to the Earth, it's very unlikely that the moon would have received all these impacts and the Earth not. We have very few craters today, but that's because we have running water which erodes the craters. So from the lunar cratering record, you might be able to figure out how much stuff fell on the Earth 4 billion years ago. Next slide. And here is a curve of the number of craters larger than a certain amount per unit area on the moon as a function of the age of the surface. How do we know the age of the surface? The Apollo astronauts and the Soviet robotic Luna vehicles brought samples of the moon back from different places. Got a sample, measure its age by radioactive dating, compare it with the crater count, and there is a correlation. And so 4 billion years ago, you know, roughly speaking, you can see the error bars, how many craters were falling per unit time, per unit area on the Earth or the Moon. And if that stuff was mainly or half or 10% comets, you can figure out how much organic matter was produced. Next slide. Well, I don't want to spend any time on this, but just to indicate that both from exogenous sources and from endogenous sources, you could calculate how much organic matter per year fell on the Earth at each epoch from different sources. And the next slide, likewise. And so then it's possible to do an inventory and see how much of the stuff there was. Can I have the lights, please? No, the lights there. Yeah, right. Thank you. So what it looks like is that there's certainly fair room for uncertainty here, but even within the range of uncertainty, there looks like there was a huge amount of organic matter on the early Earth. So much that in the most optimistic case, if you mixed it into oceans of contemporary extent and depth, you would have a solution of organic matter with about the constituency of Campbell's beef broth. Now that's a good medium for the origin of life. A few 100 million years of that. Amino acids, nucleotide bases. You might make a lot of progress for the origin of life. There's a lot of other work on the origin of life that is being done, including stuff on self-replicating RNA, a kind of nucleic acid molecule, which has the magical property of also being able to catalyze, to act as enzymes, which are otherwise all proteins. And there are experiments in which amino acids link up into things like proteins. There are experiments in which nucleotides link up into things like very short nucleic acids. In the 35 or 40 years since such experiments were first done, at the University of Chicago, by the way, enormous progress has been made, but we can hardly say that we're there at the origin of life. But at least it seems very likely that through some mix of up there and down here, of exogenous and endogenous, huge amounts of organic matter of the right kind were on the Earth at the right time. And so in this sense, we are the beneficiaries of the comets. But this is not the only way in which comets have influenced our evolutionary history. And I'd like to end with another way in which we are beholden to the comets. In what follows, I will say comets, but it's possible that what I mean is big asteroid. Suppose you were an extraterrestrial visitor, extraterrestrial survey biologist, dropped down onto the Earth for just a brief period of time, look around, examine the biology, but swiftly, make a brief report, and then on to some other planet. There are so many planets in the Milky Way galaxy, you can't spend a huge amount of time on any given one, and you will leave it to graduate students to fill in the details later. Suppose you were dropped down on the Earth, not today, but 100 million years ago, let's say. You would find an Earth rich, amazingly rich in life. But it would not be life of the sort that we are familiar with today, or at least not at first glance. Next slide, please. Instead, it would be an Earth with guys like this. Animals bigger than trees. This is the Earth of the dinosaurs. They were on the land, in the water, in the air. They had filled every ecological niche. They had been there for something like 100 million years before this time. Compare that with our species, who has been here for only a few 100,000 years. They were 1,000 times longer lived than we are up to now. This was their planet. Next slide. And some of them were fearsome hunters. Note all the little sharp teeth right there. Now, where were we 100 million years ago? Well, we weren't. Humans hadn't evolved yet. We were, at most, a possibility. Our direct ancestors were little, mouse-sized, timorous, cowering, nocturnal, insectivorous mammals. Insectivorous means we ate bugs. Nocturnal means we came out at night. Why did we only come out at night? That's why. Now, part of your job as the survey biologist of the Earth 100 million years ago is to predict the future course of evolution on this planet. Who would you bet your money on? The mouse-sized guys who eat bugs and come out at night? Or these guys, who had been around for 100 million years? I mean, not this exact species, because the dinosaurs also were evolving. I think there's no question you would bet on the dinosaurs. And yet, 65 million years ago, something happened which, in a very short period of time, geologically speaking, wiped out all the dinosaurs. Every last one of them was killed, all over the Earth, every environmental niche. And not just the dinosaurs, but most of the species of life on Earth. Most of the species of plants, most of the species of animals, most of the species of oceanic as well as land-based organisms. Some terrible, colossal catastrophe happened to the Earth. What was it? Next slide. The American physicist Luis Alvarez had the nice idea of, let's examine the atomic chemistry of the layer in the rocks corresponding to the time when the dinosaurs got wiped out. So here is a section from a famous part of the Earth's sedimentary column from Gubbio, Italy. Down here, this white stuff is chalk, generated by the microscopic calcareous foraminifera that lived in the Cretaceous seas at the time the dinosaurs were flourishing. Right? These guys took carbon dioxide from the air and made calcium carbonate shells, and then they died, and the calcium carbonate fell to the ocean bottom, and there were huge numbers of them, and over millions of years, a big amount of chalk built up. Most of the chalk that you use on your blackboards comes from these little guys who were contemporaries of the dinosaurs. The White Cliffs of Dover are made of, in England, are made of the remains of these microbes, these submicroscopic guys. Okay, so here we are, and here it stops. This is time of dinosaurs. This is not. No dinosaur fossils up here. And as you can see, there's a transition layer. Look at that, right there. And it's made of clay. And it corresponds to the time that all those organisms, including the dinosaurs, got wiped out. So naturally, we would be interested in seeing if there's anything strange about that layer. What Alvarez found is that there was an anomalously high abundance of certain atoms, of which the chief one is iridium, which is not a household word, or at least wasn't until this discovery. Chemical elements whose names are unfamiliar are most likely rare, because if they were abundant, there would be names for them that everybody heard of. The reason there isn't a lot of iridium at the Earth's surface is that it has an affinity for iron, and when most of the iron in the Earth segregated out to form the core of the Earth, the iridium was carried with it. Whereas in objects like comets and asteroids, which were not big enough to melt and do core formation, the iridium remains distributed. So meteorites that come from asteroids have lots more iridium than the surface of the Earth. So the Alvarez contention was that the reason there's a lot of iridium in here is because an extraterrestrial object hit the Earth and splashed its iridium all over the Earth. From the fraction of iridium in meteorites, you could calculate how big an object did it have to be to distribute that amount of iridium all over the Earth. And this is all over the Earth, not just in Gubbio, Italy. Dozens of places. You dig down in the sedimentary column there and you find excess iridium. The impacting object had to be, Alvarez calculated, about 10 kilometers across. That is the size of Halley's Comet. And therefore, the Berkeley group proposed that 65 million years ago, a comet or asteroid hit the Earth, and that made lots of guys die. How? Next slide. So here's an artist's view of this comet hitting the Earth. If the comet's 10 kilometers in size, and the Earth's oceans are only 3 kilometers thick, then the impactor doesn't care about the oceans. It's just the same situation as if there was no ocean. It's like one of the big impact craters on the moon, hits the Earth, carves out a huge impact crater. The impactor fragments the material that is excavated from the crater fragments, and these fine particles are blown up into the high atmosphere, and indeed off the Earth, some of it off the Earth altogether, into an orbit that the Earth gradually sweeps up and reaccretes from. It's in fact now thought that it fell not in the ocean, but on the land near the Yucatan Peninsula in Mexico. The next slide shows the result. Darkened skies all over the Earth, lowered temperatures, both of which cause much but not all vegetation to die. Herbivores have no plants to eat and also are probably not well adapted to the cold. They die. Carnivores have no herbivores to eat. They die. You can see a forlorn Triceratops, extremely unhappy. You can tell from the facial expression. To say nothing of the remains of other dinosaurs littering the landscape. He has a lot to worry about. On the other hand, I don't know if many of you can see it, but there's an extremely happy animal in this picture. Right there. See that little guy? 4 legs and a tail, and his head is up, and there's a little smile on his face right there. That guy is our great, and a large number more greats, grandparent. The death of the dinosaurs removed the principal predators, the principal enemies of the mammals. Suddenly, the world was theirs. The competition had been removed. And so there got to be a fantastic efflorescence of the mammals, filling lots of ecological niches, and this so-called adaptive radiation of the mammals, we are the beneficiary of. Let me have the lights for a moment, please. It's impossible not to have this thought. Suppose the comet that hit the Earth 65 million years ago missed it by a little bit. I mean, after all, the comets are jetting. You know, these great jets of vaporized ice come off, and just like a blown up balloon, you let it go, and then the balloon does all this weird coursing about. It's essentially the same as a rocket engine. So if there were a slightly different distribution of pockets of ice, there would have been different jetting and slightly different non-Newtonian motion of the comet, and it could have missed the Earth, could easily have missed the Earth. Suppose the comet hadn't hit the Earth 65 million years ago. Suppose that happened. Then the dinosaurs continue to evolve. So what would it be like today? So maybe, in that case, there would be a room at a school devoted to science and mathematics, and there'd be a lecturer up here on the platform, and we would all be about 9 feet tall, with lots of green, slimy scales and sharp teeth, and we would all think we're extremely handsome. And the lecturer would be imagining, what if a comet had hit the Earth 65 million years ago? A lot of our ancestors were cold-blooded, and we would have had a lot of trouble, and maybe we would, all us dinosaurs, would have been rendered extinct. And then the lecturer would say, maybe under those circumstances, the mammals would have taken over. The little mouse-sized guys who hide from us, you know, the vermin in the woodwork, it would have been their planet. And then, as a few people just did, there'd be a little snicker running through the audience at such an absurd idea that mammals could have taken over, and then the lecturer would continue on to something else, which I will now do. The next slide is a symbolic representation of a kind of dinosaur that was in fact around then, with a much larger brain for its body size than most of the extremely feeble-minded dinosaurs. And that's sort of the guy from whom if the dinosaurs had not been wiped out, the smart dinosaurs of today filling this room and on this stage might have evolved from. But the one thing you can say about the dinosaurs, of course they were wiped out, is that their extinction was not their fault. The human connection with comets, therefore, is very deep. We are, as I said several times, the beneficiary of the comets. We owe our lives to the comets. We will, of course, continue studying them. We owe our lives in the sense that the stuff from which we came from, we evolved, was partly of cometary origin, and that humans perhaps would not have evolved if not for cometary impact. We will continue studying them. Halley's Comet will be back again in 2065. We will by then, next slide please, have, I hope, substantially improved our spacecraft capability. And maybe we will have astronauts who will land on Halley's Comet and take samples back. You see, she's grabbing an extremely important collection of complex organic molecules from the comet to bring it back to Earth. And I think in the next century, some of you will almost certainly be around in 2065. So check it out. How much more we learn about comets then. The last slide I showed just for, I forgot, there is no last slide. I was about to say aesthetic reasons. Can I have the lights, please? A last thought I'd like to leave you with is this. If you take a look, just think back on this talk, which is an attempt to describe one single subject. Look how it involved astronomy, geology, physics, chemistry, even some atmospheric sciences having to do with the climate change from the dust. Anytime you look at a subject like this, you find that it's wildly interdisciplinary. The boundaries between subject matter, like chemistry and physics and so on, are made by people. They're not part of nature. The boundaries are man and woman made. What nature knows is a continuum, everything connected. You learn subjects by disciplines for the convenience of the teachers and sometimes of yourself. But nature isn't like that. Nature mixes all the sciences together. And so it's a very good thing, whatever science you're going to go into, to learn lots of different areas of science. I think it's a wonderful thing that there is an institution like this in the state of Illinois or anywhere. I think it's terrific that you have made the commitment to leave your homes at a very young age to come to a place where you can learn at a high level science and mathematics and much else. I hope the much else includes a deep awareness of the social responsibility of scientists, and I wish you all the best luck. Thank you. So, no time for questions.
Thank you. Thank you. Thank you, Dr. Sagan. Your comments have been fascinating and humbling. I might add on a personal note, you have dispelled a myth. I always thought it was chicken soup, not beef broth. We will indeed remember the first James R. Thompson inaugural lecture. And at this time, I would like to present you with a commemorative picture, which also contains your quote, and we hope that you will display it proudly on your wall in your office or wherever as a remembrance of your time at the Illinois Mathematics and Science Academy. Thank you.
Thanks very much.